Okay, so we knew it was going to come to this sooner or later. That we were going to have to, you were going to have to learn about how to count. Okay, so so counting is sort of the, it's the basis of probability theory. And so that's what we're going to talk about today. And actually, a majority of the second half of the course is about probability, discrete probability theory. Okay? So we are going to do a couple of lectures about infinity, about uncomputability, halting problem, about Gödel's incompleteness theorem. But the majority of what we'll talk about is discrete probability. Okay, so now let me say a little bit about probability theory. Okay, so some of you may already know about probability theory, but it never hurts to hear about it again because it was probably one of the greatest accomplishments. It was in the 20th century. So the probability theory predates the 20th century. It actually, the theory of probability goes back to, well, usually it's thought of as going back to the 1650s, where it was developed in a conversation meaning letters between two mathematicians, Pascal and Fermat. And Pascal and Fermat were corresponding about actually seemingly a trivial sort of issue, which was gambling. Right? So suppose you were playing a game of chance, and then suppose, moreover, that you got interrupted, something urgent came up and you had to stop in the middle. And now the question was, how do you distribute how do you distribute the wager? Right? So at the end of the game, you know who won, who lost, so who goes away with the money. But let's say that you got interrupted in the middle of the game. Okay? Then how do you determine who should get how much? Right? So presumably it depends upon how likely each person is to win given the current board situation, the current situation in the game. And so they were trying to work this out for certain games. Okay? So probability theory had its beginnings in sort of, well, basically you could say probability theory had its origins in casinos. Right? And that's what it was. It was a theory about games of chance and gambling and little puzzles, and that's what it was. That was until the end of the 19th century and the beginning of the 20th century. And suddenly, in the 20th century, it became, it sort of became the bedrock on which science was built. Okay, so it became the most important, foundation for science. And how did this come to be? Well, you see, so the way it came to be is because you would imagine that probability theory is about uncertainty. It's about tossing coins and rolling dice and dealing cards, right? Where there's chance involved. Okay? The major discovery in probability was that under very general circumstances, when the number of particles, the number of coins, the number of dice become very large, right? Then this uncertainty leads to certainty. Essentially certainty. So the point is, the chair you're sitting on has the properties it does. It has these certain properties because probability theory. In fact, there are these atoms that are moving around, there are, et cetera. You have elementary particles and so on. But in the aggregate, so the quality of the air that we are breathing, which is nothing to write home about, but okay, for whatever it is, whatever we have here, okay, so it's the result of whatever, zillions of particles, right? To be able to describe these would be almost impossible. But then, because there are zillions of these particles and each of them is behaving randomly, the aggregate behavior is practically deterministic, right? So there's some chance, there's a small chance that all the molecules in the air in this room will actually concentrate in that corner up there, and that we'll all suffocate, right? But that chance is so small, we don't even have to think about it, right? So we get certainty out of the fact that you have uncertainty at this level. So in fact, what turns out to be the case is that if you have a small number of particles, you can predict what will happen. If you have a moderate number of particles, as the number of particles gets larger and larger, it turns out it's very hard to predict what will happen. And then when the number of particles becomes very large, suddenly it becomes possible to predict again. And how do you predict? Probability theory. Okay, so this is why probability theory was so important. So, it plays a role in statistical physics. And then there was one more revolution that happened in the 20th century, which was quantum mechanics was discovered. And quantum physics is inherently probabilistic, right? So even to describe it, you had to start with probability theory. It said, the probability theory is not just a statement about our lack of knowledge about the world at large. It's actually there. It underlies everything. Now, where else does probability theory come in? It comes into inference. So basically, today, if you were to do artificial intelligence, if you were to go into artificial intelligence, and if you were to say, I really don't care about probability theory, just give me the part of artificial intelligence that doesn't deal with probability theory, where I don't use probabilistic tools. You're going to be confined to a corner like that. We were thinking about the air moving into that corner. Right, you would sort of have to move to a small corner of AI. Sort of almost every part of it is pervaded with probabilistic reasoning and probabilistic models. Okay, so this is the reason that in this course we spend so much time on probability theory. First of all, it's a beautiful theory. Second of all, it has provided a lens through which you can look at the world. And it has really determined our view of the world for over a century. And thirdly, it's really revolutionized how we think about computer science. So if you go into AI, you're really doing probability theory. If you're working in systems, you do load balancing, probability theory, hashing. So it sort of pervades across our field. If you're doing algorithms, we'll talk about probabilistic algorithms. So you really have to understand this to understand various parts of computer science. Okay, so all right, so okay, but before we can start on probability theory, we have got to learn how to count. And okay, so where does the counting come in? So the place where counting comes in is this fact that, even if you have a relatively small number of coin tosses, so let's say you toss a coin 100 times, and you want to know how many possible outcomes do you get. well, that number increases exponentially in the number of tosses, in 100, right? So it's 2 to the 100. And basically, in probability theory, we talk about, we have n particles, n dice, n tosses, whatever. And we want to know what kind of outcomes do we typically see. But which are the typical outcomes? What do we expect to see? How many heads, how many tails? But the number of possibilities, the number of possible sequences we'll see is very, very large. Okay? And so somehow, even to get started in probability, you've got to learn what kind of sequences do you expect to see? How many of them are there? And that's what determines probabilities of events. Okay, and so let's start at the basics. So we are going to talk about counting. And we can phrase this in one of a number of ways. So the first way we can phrase it is the following. So we are given a population. Okay, so we are given a population, and maybe this population happens to have 6 individuals in it. Maybe we label the individuals 1, 2, 3, 4, 5, 6. Okay? And then what we do is sample this population. Okay, so when we sample this population, we sort of reach in. So we think of this as a bag. We reach in and we pick out one sample. So maybe our first sample happens to be 2. We reach in, pick out a sample again. We might get the sample 1. We reach in again, we might get 6. We reach in again, we might see 1 again, and so on. Okay? So this is called sampling with replacement. With replacement because, when we reached in the 4th time, it was, we could get 1 again because after sampling, we throw that individual back into the population before we resample, right? So this would be a model of for example, rolling dice, right? So either think of it as rolling 4 dice or rolling 1 die 4 times, right? So this gives you how many outcomes there were. Okay. So now what we'd like to know is how many possible outcomes are there, right? So how many possible, if we roll a 6-sided die 4 times, how many possible outcomes would there be? 6 to the 4, because so the claim is that the number of possible such samples would be 6 raised to the power 4. Okay, there's another setting in which we could be playing the same game. Let's say where our population now has somewhat more points in it, and let's call them C sub 1, C sub 2 through C sub 52. Okay? And this time we sample, and maybe we got C sub 20, C sub 15, C sub 2, C sub 40, C sub 25. But in fact, in this case, once we draw a sample, we don't throw it back in. We keep it with us. Okay, so this is called sampling without replacement. Okay, in this case, our population might be a deck of cards, and what we are dealing is perhaps a poker hand. And now again, what we'd like to know is how many possible such sequences are there? Yeah, so maybe just going a little more slowly. So how would we even think about this problem? So how would we count from first principles how many such possibilities are there? So it would seem that after you draw the first card, it changes what the possibilities are for the second one. And after you draw the first two, it changes the possibility for the third one, and so on. Right? So the main point here is that even though the first card changes which cards are possible to draw on your second try, it doesn't change the number of possibilities for the second card. Right? The number of possible, the number of choices for the first card is 52 because you had a population of size 52. But now, no matter which card you drew, no matter which one this was, you cross off one of these possibilities. And so you're left with 51 choices for the second card. And now, again, no matter which two cards you drew, they're exactly, you cross off exactly two of these entries. And so there are exactly 50 possibilities for the third one, and so on. Okay? Now, let me just say one thing. So I'm sure many of you have seen this before, and this is sort of a review for you. But, once we get through counting, counting can be quite hard. Counting is not, well, okay, so let me restate it. Counting is actually very simple, but unless you understand the basic principles well, it can look very hard, right? So if you don't want it to look very hard, then you really have to understand what the basic principle is, because once we apply the same principle in a different setting, it won't look that simple to you again, right? If you really understand this principle, it'll be equally simple. You'll sort of see that in this other setting, we are really using this same principle over and over again. Okay? So what we said here is that the number of ways of drawing this sequence of cards is 52 for the first one, 51 for the second, 50 for the third, 49, 48. Okay? And so there are that many possibilities. So it's would you say that's about 10 to the 8, roughly, give or take? Right? So already, this number is reasonably impressive. Right? 10 to the 6 is a million, so it's a tenth of a billion. It's 100 million. Okay, so what we just did, it's called the first rule of counting. And what it says is, if you are making up an object through a sequence of choices, so you're building an object, where there are n sub 1 ways of making the first choice, n sub 2 ways of making the second choice, no matter what the first choice was, n sub k ways of making the kth choice, no matter what the first k minus 1 choices. then they are exactly n1 times n2 times nk objects. Yeah? So it's clear that this is what we are doing. We're saying you're building up this sequence of cards by picking, making a sequence of choices, or you're rolling dice by making a sequence of choices for each die. And then we said, well, there are this many ways of making the first choice, this many ways of making the second choice, no matter what you chose first, and so on. Well, then the number of, total number of things you can choose is the product. Here's another way of saying it. This is in terms of, so this is the first rule in terms of trees. Okay, so here this is where we start from. And now we are saying, we are trying to pick a path, but our first step, we have n sub 1 choices. Okay? And now, no matter what we choose, no matter which of these choices we make, there are n sub 2 ways of making a second choice. Okay? And then we are saying, no matter what we've chosen, no matter which of these we've chosen to go along, for each of these, there are n sub 3 ways of making another choice. And so on, right? All the way down to n sub k. Then the claim is that the number of possible places you can end up in, which is the leaves of this tree. These are called the leaves of the tree, the ones, the endpoints, right? So you're walking down, you follow any old path that you want to, and then you end up down at the bottom, and you want to know how many possible places could you end up at. So this number of places you can end up at, which is the number of leaves of the tree, is equal to n1 times n2 times so on, nk. Yeah. I'm sorry? Well, no, this is just a technique, right? So it says, suppose it's the case. Suppose you're trying to count something. And suppose it's the case that you make a sequence of choices. But it has this property that your first choice, well, you have this many possibilities. Okay, you have this many possibilities. But then we are saying, no matter which of these you choose, if it's true that you now have the same number of choices for your second, for the second step. Okay, and then we are saying, suppose, moreover, it's true that no matter what you did so far, no matter which, if you're at the fourth level, no matter where you've reached on the fourth level, you have exactly the same number of choices.
But this doesn't apply to all counting problems.
It doesn't apply to all counting problems. Yeah. This is just a simplifying principle, which we can apply in many, many cases. Okay? In some cases, we can apply it directly. In some cases, we have to be clever, and instead of looking at the problem straight on, we have got to tilt our head or look at it upside down or something. And then we can say, oh, yeah, now we can see the structure emerge. So we can apply the first rule of counting. Yeah? The reason it's called the first rule of counting is because there are more rules of counting. Okay, and those sometimes help us. The second rule of counting sometimes help us sort of say, well, we want to count this object, but But instead, we'll count this other thing, the number of possibilities for this other thing, to which we can apply the first rule. And now we'll apply the second rule to do something different. Yeah? Okay. By the way, there are other ways we can think of counting problems. There are other formulations as well. Actually, does anybody, can somebody tell me what the time is? 4:13. Okay. And is it me, or is it really warm in this room? More than usual. Yeah. And okay, does that make a break seem more? Yeah. Okay, let's take a break. Okay, so here's another way you can look at these counting problems. Okay, what we looked at so far was the sampling model. This is called the placement model. So in the placement model, you're given a bunch of boxes. Okay. And so let's say you have n boxes. And you have k balls. And what you want to do is you want to place these balls in the boxes. And you want to count how many different ways are there of doing this. So you have balls number 1. Okay, so the balls are numbered 1 through k. What you want to do is you want to place the k balls in the k boxes. And you want to know how many ways are there of doing these placements. Okay, so I claim that this is almost the same problem as a sampling problem. You just have to know how to translate between the two. So okay, maybe you want to take a minute or two to think about it. So think about why this is the same problem as the sampling from a population problem. Okay. maybe ask your neighbor. Okay, so let me just say something that, this kind of thinking that you're going through to say, is this process the same as the other one? This is an essential part of a field called, well, combinatorics, which counting is a part of. It's sort of, there are many aspects to it, but one aspect of it is this, where you're looking at something and then you say, if I were to look at it like this, it's the same thing as this other process. And therefore, I don't have to analyze this again. It's the same as that one, right? And so this is sort of it's a completely fundamental part of this area. And if you can, if you feel you have a talent for this, then use it, because it'll make things much easier for you. If you feel you can, if you feel you can do something to be passingly good at it, again, do it. Sort of try to practice it. This is it's something that it's not an inborn ability necessarily. It's something that you can acquire with some practice, and it's also a lot of fun. When it's it's the same sort of thing that happens when. When you see an unexpected result or a joke, what is it that makes jokes interesting is because it's looking at something in a different way. That's what humorists do. And it's that same sort of pleasure you can derive from seeing things from a different viewpoint and saying, oh yeah, I don't have to do a complicated calculation here. I just look at it like this and it just solves the problem for me. Right? So, okay, so in this case, what are we doing? Well, we have the K balls, which we are placing into N boxes. And now, let's just look at this. So we place the first ball into this box, and we think of it as, what did we do? The ball was our sample that we picked. And which sample did we pick? From the population, we picked the second sample. So our population consisted of the boxes, and which one we actually sampled was the ball. Right, so we so in other words, the balls are empty slots where we are putting our samples down. Right, so the boxes correspond to the individuals in the population. And the balls correspond to the individual samples. Okay, so now here's another question. What do we mean by with replacement and without replacement? Yeah, do you want to think about it for a moment? So remember, in the case of the population, we were saying we were sampling from the population, and with replacement was like fishing, right? You fish, and then you're supposed to throw the fish back in, right? If you do it, if you're being nice about it. Okay. Without replacement is when you're catching fish to eat. Okay, so what's the corresponding thing here in the placement model? Yeah, do you want to think about it for 30 seconds? Okay, so the reason, okay, so think about it, and then I'll say why yeah. Uh-oh. Oh, no. Okay, so sorry, let's go over it. So in this context, remember the individuals are the boxes. The sample is a ball. So if you have two balls that land in the same box, that means that you've sampled that individual twice. So, which means you're obviously doing it by replacement. If you can place more than one ball in the same box, that means you're sampling with replacement. If you're allowed to put only one ball per box, then it's without replacement. Right? So without replacement corresponds to either 0 or 1 ball per box. Right? So at most 1 ball per box. Now, let me say one other thing about how to think about these things, right? One thing you might, you'll experience as you start working on this is, if you just passively try to read this stuff and try to, without actively working it out, it's much, much harder. Okay, so there are some things where you can sort of sit back and say, just show me how it is, show me the picture, rather than you're working it out. And maybe that's the most efficient way to do things, because maybe the work is in creating the picture, and then you can sit back and sort of say, okay, yeah, I like this one, it's a nice picture, etc. Right? In some things, in some cases, that picture is then very hard to understand, whereas if you just actively work it out, it's much simpler. And that's the case here. Right? This is one place where if you're going to passively sit back, you're just making things really hard for yourself. Okay? It's usually hard to learn passively, but in this case, it's particularly hard. So be active, because that'll simplify things. Do you have a question or no? Okay. Okay. So, by the way, how are we doing on time? Okay. So let me do one more model. So it turns out there are many, many models for counting, and they all turn out to be the same. Okay, and okay, so there's the physics model. Okay, so in the case of the physics model, you can still think of it as placing balls in boxes. So you have a bunch of balls, a bunch of boxes. But now, the balls correspond to particles, and the boxes correspond to states, the possible states of that particle. So for example, your balls might correspond to particles like electrons or something like that. States are, is it in the ground state, excited state, etc. Or your balls might correspond to atoms in a gas, right, or molecules in a gas. And states are whatever, is it Is it moving right? Is it moving left? Is it fast, slow, whatever, right? So it's in one of many possible states. Yeah. Now, what does without replacement correspond to? Okay, so remember, without replacement corresponded to saying at most one ball per box. You cannot place more than one ball in a box. In the physics model, what it says is you cannot have more than one particle in that same state. Okay, this is what shows up in quantum mechanics. It's called the Pauli exclusion principle. This is what says that, you know, your electron orbitals, you can have only one in each. And the resulting probabilities are called the Maxwell-Boltzmann statistics. Okay, so this is just to give you, none of this is stuff that you need to remember. It's just to give you a sense of, how powerful, how all-encompassing this, it's a very simple topic, counting. It's elementary, but it has a far-reaching influence. Okay, we can do it for, we can study it for various reasons. But in fact, once you move forward with this, and if you get far enough into, let's say you got into your PhD program in statistics, in artificial intelligence, and you did statistical machine learning theory or statistical machine learning. Well, you might not do any of this, but pretty soon what you would start realizing is that many of the algorithms that you're working with, or much of the formalism that you're working with, actually got borrowed from some of the physics. Right, so it's actually a much more well-connected field than you would imagine, right? And so these connections, even though they are still far away, someday if you go far enough into it, you'll find these connections. Okay, so let's get back to the nitty-gritty. So there's a function that I'm sure most of you know about, but we really do need to understand in this context. We need to understand factorials. So n factorial is n times n minus 1 times n minus 2 times 1. Right? It's just you just look at that product. What we said is, if you're sampling from a population, and you sample k individuals from a population of n, but without replacement, then the number of ways you can choose those k individuals is n times n minus 1, so on, times n minus k plus 1. Right? So you have k different terms here. The first one, there are n choices. Second one, n minus 1. Kth one, n minus k plus 1. Right? So for example, if k is equal to n, then this is exactly n factorial. But in general, you can write this as, you can multiply the numerator and denominator by something, and then you can write it as n factorial divided by n minus k factorial. Right? Because n minus k factorial is exactly what you need out here to continue this all the way down to 1. Okay, so now you're ready for the second rule of counting. What the second rule of counting says is if you're trying to count the number of sheep in a field, and if it's too hard to count the number of sheep, then count the number of legs and divide by 4. Okay? So what it says is, suppose you're trying to count the number of, suppose you're trying to count say the number of unordered objects. But it's too difficult to do it. Then okay, so suppose you're, okay, let me say this a little bit better. Actually, why am I bothering to do this? Let's first do an example and then come to the actual rule. Okay, so let's go back to the example that we had before of a poker hand. Right, so we said we have a population of 52 cards, C1 through C52, and our poker hand is a set of 5 cards, right? It's a poker hand consists of 5 cards that are dealt out to you. Now we want to count the number of poker hands. Okay, so so we can count it. There are 52 choices for the first card, 51 for the second card, 50 for the third, 49 for the fourth, 48 for the fifth. What else is there to do? Well, so imagine that you had, this was, 4 of hearts, 2 of, is this what clubs looks like? 8 of diamonds. Diamonds is easy to draw, so let's draw more of those. And but queen of hearts and ace of diamonds. Okay, so that's what we got dealt, and now, okay, so there are this many. There are 52 times 51 times 50 times 49 times 48 such sequences. We know because I mean this is what we said. It's by the first rule of counting. But now, suppose that instead of this, you got dealt this different hand, which was 8 of diamonds, 4 of hearts, queen of hearts, 2 of clubs, and ace of diamonds. Well, this is obviously, we said that there were 52 choices for the first card. This was one of the 52 choices. And we said no matter what you're given, there are 51 choices. Well, that's one of the 51 choices, and so on. Right? So when we counted this number, we were saying that hand is different from this hand. Right? But actually, it's not a different hand of poker. Because when you're dealt a poker hand, all you care about is which 5 cards you got dealt, not which order you got dealt them in. Well, it depends upon which way you're playing poker, but right, if it might matter in which order you're being dealt the hand, it may not matter. But say for now that we are just saying you just get dealt all the 5 cards face down, you look at them, and then you play. That's not, that may not be the way you actually play in practice. There are many, many ways of playing poker. But let's say this is the way we are playing it. It matters to us what this set is. We don't care in which sequence the cards happen. So now how do we count the number of hands, where hand is the set, not the sequence? Okay, so this gets quite complicated, right? Because now the first rule no longer applies. You see, so the fact that that we can apply the first rule of counting, this is a very special circumstance. It has to be the case that we are building an object one choice at a time, and that there are exactly this many ways of making the first choice, and then no matter what we chose, there are exactly this many ways of making the second choice, and then no matter what the first two choices were, there are exactly this many ways of making the third choice, and so on. That's a very special circumstance. We've got to sort of maneuver to make this happen. Here, when we say that this is the same as that, we have no hope of making that first rule work until we realize that what we should be doing is not counting the number of sheep, well, where we think of that and this as the same sheep, right? But counting the number of legs, which is, well, we think of that as one of the legs of the sheep and this as another leg of the sheep, right? But that's okay. If we count the total number of legs, that's easy to do because then we count this as different from that, and we already know how to count those, right? It's the number of all sequences of poker hands, where the order does matter. And then, now what we've done is we've restored this property that there are exactly 52 ways of choosing the first of these objects, to make the first choice. There are exactly 51 ways of making the second choice, no matter what we chose for the first, and so on, right? Okay, but then the second thing we need to do is we need to figure out how many legs are there per sheep, because that's what we're going to divide by, right? So how many ways are there of taking these specific 5 cards and rearranging them? How many different orders could they be dealt out in? Exactly 5 factorial, right? Because you could take, now you're choosing from these 5 cards and you're saying, which one came first? Well, there are exactly 5 choices. Which one came second? Well, no matter which one you chose to go first, there are exactly 4 choices for the second one. Which one goes third? Well, no matter what you chose for the first 2, there's exactly 3 choices, and so on. Okay, so what we're saying is the number of legs is 52 factorial divided by 47 factorial. Is that right? The number of legs per sheep is what? It's 5 factorial, right? Once you have one of these objects, and then you say, once you know the set of cards, and you want to reorder them, right? How many ways are there of reordering them? Exactly 5 factorial. So then you say, well, the number of sheep is exactly 52 factorial divided by 47 factorial times 5 factorial. Okay? Now this number is, this way of writing something is so, it's so pervasive that there's actually notation for this. What this is called is, it's written like this. It's written 52 with 5, and you read it as 52 choose 5. So it's a number of ways of choosing 5 individuals out of a population of 52. Yes? So we can repeat the same same reasoning and say, suppose instead of 52 cards we had n, we had a population of size n, and suppose instead of choosing 5 individuals we had to choose k individuals, then what's the number of ways of doing that? So if you have n population of size, if you're choosing k out of n, the number of ways of doing it is n choose k, which is n factorial, n minus k factorial, k factorial. Yeah? Sorry, how are we doing on time? 4:43. Oh, good. Okay, we have some time. So, so let's do another example. So suppose that you had to deal a hand, deal a game of bridge. Okay, so if you're playing bridge, you play it with 4 players. Each gets 13 cards. Right? So how many different ways are there of dealing a hand of bridge? Right? So you're dealing out all 52 cards to 4 players. Right? So how many different ways are there of dealing these cards to the 4 players? So let's try to imagine what we want to happen. So you have your 4 players A, B, C, D. Actually, how are they called in bridge? It's called they are usually called east, west, north, south. That's what they're called, right? Okay, so you're going to deal out 13 cards to each one. Right? And you want to know how many ways are there of dealing out these cards? How many different possible games could you have? Right? So what do we do? How do we count that? Let's use the second rule of counting. What does the second rule of counting say? Yeah, so here's what it says. So what it says is, if you want to create an, so what's the case out here? Well, we've dealt out 13 cards to West, but it doesn't matter in which order you dealt them to him. What matters to West is what the 13 cards are as a set, not as a sequence. Similarly, you have dealt 13 cards to South, but what matters is what's the set of 13 cards. Right? The second rule of counting says, if you're counting these number of configurations of this kind where somehow order doesn't matter, right? So where some of these configurations for your purposes are the same as others, then pretend that they are different from each other. Pretend that the order does matter and count how many such there are. And divide by a number, which is the number of ordered objects per unordered object. Right? So meaning, in this case, we are dealing out 52 cards. We'll pretend that we are dealing out these 52 cards, and exactly which order we dealt the cards in matters to us. So there are exactly 52 factorial ways of doing that. And then what we're going to say is, actually, out of these 52 factorial ways, objects, there are many objects that correspond to one object of our choice. Right? So we'll say, if you take these 13 cards that South has and you scramble them in any way, it's all the same to us. It's the same object. It's the same unordered object. If you take the 13 objects that East has, you scramble them up, it's the same object. Right? It doesn't make any difference to us. So we count for one of these unordered objects, how many ways are there of creating an ordered object? And we divide by that. So is this clear to everyone? Is it clear what we are trying to do, what the second rule of counting is? Yeah? Yes?
So the first step is the same as poker, except with 13 cards. Is that right?
Well, so what was the first step in poker? Okay, so let me just say there are two ways of solving this. Let me just go through both of them, right? So just so you have a way of understanding it. Do we have 15 more minutes? Or? Okay, so actually let me give you a couple of minutes to think about this problem first, and then I'll go over two ways of solving it. Okay. Okay, so here's what we have to do to solve this problem, right? We've got to figure out what our unordered object looks like and what the ordered object looks like. So what's the unordered object look like? Well, to understand the unordered object, what we have to do is we have to pick a subset of the cards, right? So we have to pick a subset S sub n, S sub w, S sub south, S sub east. These are a subset of the 52 cards, 1 through 52. Oh yeah, sorry, it looks strange to call the cards 1 through 52, but what I mean is ace of clubs, etc., but there are 52 of them, so let's call them 1 through 52. So first, this is what the unordered object looks like. It consists of 4 sets, right? Which set is which matters, but what's within the set, it consists of 4 sets such that each of them has exactly 13 elements, right? Such that, remember, this is how we say the number of elements of the set. So each set has exactly 13 elements in it. Right? So we start with a set of 52 elements, and then we create 4 sets, each of 13 elements, the disjoint sets, so on. We partition it into 30. Okay. So this is what our unordered objects looks like. What does the ordered object look like? Well, what we do is take all the cards in each set and you place them in a certain order, in the order in which they were dealt. Right? So now instead, so that's S sub n, except it's ordered in this way. And similarly, S sub w, similarly S sub s, similarly S sub e. So you just order each of these in a certain way, right? And now if you take two of these elements and you swap them, if you move this one there, you'll call that a different object. So now, how many ordered objects are there? Well, clearly, to count the number of ordered objects, well, you just have your 52 cards lined up in some order. How many different orders are there? Exactly 52 factorial, right? That was the simplest of those counting problems, so it's exactly 52 factorial. Right? Now, for each of these, the second thing we want to know is, for each of the unordered objects up there, how many ordered objects are there? Okay, so what do we mean by this? How many of you, okay, so meaning I have 13 cards, right? You have 13 cards. There's somebody here who has 13 cards. There's somebody there who has 13 cards. We've already dealt these cards, right? But now we want to know how to create these ordered objects out of this. So I'll take my 13 cards and I'll place them in order. How many ways can I do that? 13 factorial, right? How about you? How many ways can you place your 13 objects and cards in order? 13 factorial. How many ways can we together place our hands in order? Right? It multiplies because for every way that I place my cards in order, which means 13 factorial of them, for each of those, you have all your choices, right? By the first rule of counting. So we are using the first rule of counting here, again. So it's 13 factorial times 13 factorial times 13 factorial times 13 factorial, right? And so what's the number of unordered objects? So by the second rule of counting, it's this divided by that. Right? So the number of bridge hands is 52 factorial divided by 13 factorial whole raised to the power 4. Okay, there's another way that you can count the same thing. What you can do is you can say, look, I have 52 cards to begin with. Right? What I'm going to do is, out of these 52 cards, I'm going to choose 13 to give to you. Okay, so that's 52 choose 13. Second rule of counting, right? 52 choose 13. Okay. Now, how many cards do I have left over? 39. So now we have 39 cards left. I'm going to give myself 13 of these 39 cards. How many ways are there of doing that? 39 choose 13. it doesn't matter which cards I gave you, right? There are 39 left over, and there are 39 choose 13 ways for me to get those cards, no matter what 13 cards you got, right? So first rule of counting says we multiply these numbers together, right? Now there are how many cards left over? 26 left. Now we're going to take 13 of these cards and give them to that door out there. So 26 choose 13 ways of doing that. Now there are 13 cards left. How many ways are there of choosing 13 to give? 13 choose 13, right? So the total number is 52 choose 13, sorry, 52 choose 13 times 39 choose 13 times 26 choose 13 times 13 choose 13. Now, it should be the case that this is the same thing as 52 factorial over 13 factorial to the fourth. What are the chances of that? So let's see. Okay, so this is 52 factorial over 13 factorial times 52 minus 13 is 39 factorial times 39 factorial divided by 13 factorial times 26 factorial times 26 factorial divided by 13 factorial times 13 factorial times 13 factorial over 13 factorial times 0 factorial. So you have to say that 0 factorial equal to 1. Okay.